recording just now. Thank you for remembering, Martin. Hi, guys. This is the recording starting when Martin forgot, but we're only on the second slide. Ooh, I forgot a lot later one day, and it wasn't a good thing. So having said that, let's move on. This is copyright 2018 DBI. Okay, next thing. Today's show, we've got quick announcements as always. We've got some audience polls, and then we've got Jules' great presentation on total recall and exploiting in-memory features in Db2 for ZOS. Audience Q&A will come through at any time. There is if you've been on the show before, you know there's a questions tool available to all participants. Please write your questions in there, and I will monitor that queue and interrupt at the right time to give Jules a bit of a break and to have some interactive capability in the session. So with that, moving along, I have some good news. We've got some sessions coming up scheduled with speakers, and I announced last time we had Terry Purcell from the IBM Silicon Valley Lab. He's talking about machine learning exploitation, but he's mainly doing that around optimization. I've looked at his presentation, and it's really cool, and that's a must-see show next month on the 16th. On the 14th of December, we've got another IBM Gold consultant, Christian Malero, will be joining us from Belgium, and he'll be talking about distributed access. And, that also will be a great show. Just advertising for myself, I'll be on the Db2Night show on the LUW side, talking about indexes versus prefetch and how to win the fight. And in the new year, I don't have topics yet, but we do have speakers lined up for January and February. We've got Dave Belke coming back to present with us, as well as Kai Skro from UBS Heiner. So we also have dates available, or we know our dates. They're mainly mid-month from March until June, and I'll be lining up speakers for those, and I'll make that information available. I will be putting the information to register for Terry and for Christian up this afternoon as I complete the pre-processing of today's show. So please look for that and sign up as you will very shortly. Oops, and I forgot to update today's date, the date for Scott's show. I know it's not the 20th of September. I understand that was a good one. I knew I would forget something today. It's just been that type of week. I've been heads down marking data modeling assignments for the university class I'm teaching at Seneca College here in Toronto. And I knew I would forget something. It just had that inkling. So I'll have to look up that date and announce it later on in the session. And I am actually being, one of the other things distracting me at the moment is my silent partner, who is fortunately very silent these days. He doesn't seem to bark as much at doorbells and at squirrels, and that sort of thing, but he still is around and reminding me that one of the ways to keep him quiet is to keep putting liver treats in his mouth. And so there's Charlie again. If he does go off, well, now you know who he is.
I am here still, Martin, listening carefully.
Yes, you can chortle at my Charlie jokes. Those are the best jokes I got today, I'm afraid. As the old saying goes, if you can't remember a new joke, do an old one. Here are our sponsors, as always. We don't take time to do a commercial on the Z version of our show, but we just mentioned the people that have helped us. And, of course, Triton's is on there as a valued sponsor of the Db2Night show. All right, now it's time for our polling questions. Let me pop those out, and we'll get right to them. So the first thing we're going to do is the standard one is what version of Db2 on ZOS are you running? And we only get 5 choices, Jules, so this is the way I decided to break it down. And notice that version 10 has gone away now. We no longer talk about version 10. Yay. Time marches on. Okay, we are up to nearly 30 seconds, and we've had 73% of our audience voting out of the 50 attendees so far. So I'm going to close that off and share the results. And we notice that 2/3 of our audience roughly is in new function mode, and we have the other 31, almost the entire audience is either version 11 new function mode or version 12. That's great news.
Yep, great.
Yeah. Only a few stragglers today. All right. What other DBMSs do you have? Again, another one of our standard questions. Well, people answer that. I am feeding your old Charlie more liver. This dog should actually weigh 80 pounds rather than the 8.5 pounds he does weigh, based on the amount of treats he has. And this time we have around 80% of our, 85% of our audience has voted. That's fantastic. Let's have a look at that. As expected, we have a large contingent of Db2 LUW people joining our show, and we still have people on VSAM, and we have all of the other collectors series of DBMSs out there, I'm sure. I worked at one place where we only had 8 DBMSs installed. How could we get any work done with only so few? And what Z Systems hardware generation do you have? And this is also looking very promising. We've got a very up-to-date audience today by the looks of things. And that's really great. Oh boy, we've got people are voting fast today. I'm closing this and moving on because we had 88% of our audience. They're quite attentive today. So there we have, most people are on Z14s and then Z13s, and then the rest tail off. With some people don't track that stuff, and only a few people on older hardware. That's great. And we have one last question to do right now, which is to look at the size of the buffer pools that people have. And there we're going, getting that one done. We'll have to think about this. This is might involve even having to, if they really wanted to be accurate, they might have to look something up, but it'll give us a good idea here. We're at 75% of the audience. Thanks for voting quick, guys. I appreciate gives us more time for the session. And with that, we're up over 80%, which is our normal cutoff, so I'll share the result there. And there's the numbers we have. 31% are not dedicating anything, and 38% are unsure of the total size, but they do have some, and then we have some that have a lot of memory, which is a beautiful thing. Okay, I'm going to close that off and put that away. And I think I need to go back in there for just a minute and hide those results so that my screen should pop up again. And I can get along and move the things forward. You should be, are you seeing my screen again, Jules?
Still seeing the poll at the moment.
Are you?
Yeah. Back to your desktop now.
Great. So I'm at the point where we're going to turn it over to you right now, and you will become the presenter, and then we can move on. So this is going to be our great session today.
Okay, so thank you very much, Martin. Apologies for not participating much during the preamble. I don't know whether there's a connectivity issue my end, but you did keep fading in and out a little there, but hopefully everybody can hear me.
I'll let you know when you can't, but that's one of the things.
Okay, great.
That's one of
good morning, good afternoon, good evening, everyone, wherever you are. Thank you very much for taking part in today's webinar of the Db2Night show. As Martin said, my name's Julian Stuhler. I'm a Db2 consultant based in the UK, and I'm going to spend the next 45-50 minutes or so talking to you about some of the new features specifically around in-memory in Db212. certainly one of the major headline features that IBM have spent a lot of time and effort putting into the new release of DB2. Of course, I called it the new release of DB2. Version 12 has now been out for a couple of years, so it's new to most people, but really in terms of the marketplace, it's been around for a while now. So before I continue, I really ought to just spend a few moments with some acknowledgements, particularly to the first two people on the list here. So Nina and Peter are two of the developers for the in-memory features, in particular the fast reverse block feature inside DB212, and they were very kind in giving me some of their time to help me better understand some of the internal workings of the fast reverse block feature so that I could kind of boil it down into the essentials that form the base of this presentation. So thanks very much to Nina and Peter for being very patient with me while we went through those details. Okay, I'm going to skip briefly through my introduction because it's all inside the bio that's available with this webcast anyway, and I want to spend most time talking about the actual technical detail in here. So I'll spend a bit of time just in terms of positioning where IBM and the industry in general is going in terms of a big memory and in-memory database in general, and specifically around IBM's moves to provide the ability for customers to be able to afford and configure greater amounts of real storage on their machines so that things like the new features in DB212 can be used to potentially drive down CPU usage for big transaction systems. We'll then talk specifically about the two major in-memory features of DB212, so fast reverse blocks and contiguous buffer pools. I'll mention a few other features as well, but we're really majoring on those two and fast reverse blocks in particular within this presentation. And then at the end, I'll give you a few practical guidelines in terms of things that you can look out for, ways in which you can configure this. Still very early days in terms of real customer experiences in high production workloads for these features, but we expect those to be refined and expanded a lot more as we kind of hit the main bow wave of people moving to DB212, and in particular the new function activation that's really needed to use these features in a data sharing environment. Okay, so I'm going to skip through my introduction and go straight to the background here in terms of the big memory era. And I use this slide in an awful lot of presentations now, actually, because it kind of encompasses on a single page the last 5, 6, 7, 8 years worth of history in terms of both the hardware, that's the chart on the left, and the software, DB2 in particular, and that's the chart on the right. So just starting off with the hardware side on the left, you can see the various columns we've got here. I've got the last 5 generations of IBM Z series machines, going all the way back to the Z10 through the 196, the EC12, the Z13 and Z14, Z13 and Z14 if you're on the other side of the Atlantic. And just looking at the poll that we had earlier on, it was very good to see that a lot of you guys, the audience, are on the highlighted items in red at the bottom here, the Z13 and the Z14. Next column is looking at the maximum amount of memory we can have on each KEC, on each physical Z series server. And you can see back in the Z10 days, the maximum amount configurable on a physical server was 1.5 terabytes. That doubled when we went to the Z196, stayed the same, but then tripled again with the Z13 and has tripled again in the Z14. So just in terms of the maximum configurable memory within a single physical machine, it's absolutely clear that the trend here is for IBM to be allowing ever bigger amounts of real storage to be configured for these machines. And then looking at the individual LPAR, the logical partition level, on the third column here, we were limited to 1 terabyte right the way through until the Z13. And then from the Z13 level onwards, we now have the ability to utilize up to 4 terabytes of storage in any physical, on any logical partition, any LPAR within that machine. So I'm talking about ZOS LPARs here. As per the footnote on at the bottom of the page here on footnote 3, some OSs, such as ZVSE, are able to go much higher than that. And in fact, ZVSE can actually go up to that full 16 terabytes, which is the LPAR architectural limit currently. So again, very clear trend here. More storage available per physical machine, more storage available per LPAR inside that physical machine. Now that would be all well and good if possible for you to go and configure this stuff. You need to be able to afford to actually specify this and be able to buy that memory when you actually go away and do an upgrade on your machine. And that's really what the fourth column here is. It's the look at the average cost, a street price, average cost per gigabyte of real storage for each of those generations. And again, you can see at the Z10 era, we were looking at $6,000 US for a single gigabyte of storage in these machines, which is incredibly expensive if you compare that to the kind of memory that we stick inside our PCs and servers today. Of course, this is a very much higher spec memory than we use, but still a huge potential cost there to go and configure a terabyte to 1.5 terabytes of that storage would cost a lot of money. In the Z196 level, then there was a 75% reduction, and that went down to about $1,500 per gigabyte, which is obviously a major step in the right direction in terms of customers being able to afford higher spec machines. But it was the Z13 where we really saw another step change here, where there was another 80% reduction, and the average street price for Z13s is around about $300 per gig. Still expensive compared to the memory put in our own machines, but now much more reasonable and much more feasible for customers to start really pushing the boundaries in terms of speccing up the memory configurations they get when they order an upgrade to their Z13 or Z14 levels. Now, of course, I am actually seeing customers now, many of my customers are on Z13, Z14, and I am actually seeing those customers exploiting these price breaks now, and it's not uncommon now to see much higher memory footprints on newly configured systems than typically we'd see even a couple of years ago. So I think the hardware picture here on the left is fairly clear. Ever increasing amounts of memory per physical machine, ever increasing amounts of memory per each logical LPAR, and that memory is becoming cheaper and cheaper with each generation, which is allowing customers to configure their machines with ever higher amounts of storage within them. On the right then, looking at the Db2 perspective here, as we go through the various releases of Db2, you'll see going all the way back to version 9, version 10, version 11, we're always limited to a maximum of 1 terabyte in terms of the total buffer pool size. That's all of the buffer pools for a given subsystem added together. The maximum was limited to 1 terabyte. Just look at the footnote there in footnote 5 as well. That is also subject to a maximum of twice the configurable LPAR storage. Of course, in production environments, you would never over-configure your buffer pools so that you're over-committing them to the extent that you've got twice the size in your buffer pools and you've actually got real storage. You're going to get a lot of problems significantly with paging issues there. But this is a hard limit that's put on Db2 to stop you going any further than that. You wouldn't go anywhere near that kind of multiplier in normal production systems. But the reason that chart is there at all is because version 12 changes the game entirely. We've got a 16 times increase in terms of the maximum amount of buffer pool storage that can be configurable in a version 12 system, gone up from 1 terabyte all the way up to 16 terabytes. And again, this is a real indication that IBM is serious about the whole in-memory thing. Not only is it providing that capability on the hardware side, it's also providing that capability on the software side in terms of being able to physically exploit much greater amounts of storage within the Db2 environment. Now, the more sharp-eyed among you will see that we've actually got a bit of a mismatch here where Db2 is able to potentially use up to 16 terabytes of storage in a single system, but we've got this architectural limit in ZOS where we've got only 4 terabytes available on a single LPAR. So clearly Db2 is somewhat ahead of the curve here at the moment, and this is IBM positioning Db2 to be able to exploit much larger LPAR sizes in the future. And I think it's reasonable for us to look forward and consider that when we get the next iteration of the hardware, we're likely to have even greater numbers in terms of the maximum amount of memory per KEC and per LPAR. So moving on in terms of where we are. Moving on in terms of where we are for the big memory exploitation here. We had we had a problem in version 10 with virtual storage. That was typically the gating factor inside the real storage allocations for people. So in terms of the ability to be able to scale up our systems, virtual storage was always the consideration in terms of version 10 maximum amount of applications and workload you could put through. That's no longer a major constraint. Now it's moved from virtual storage onto real storage, and now real storage constraints are typically is what will limit us in terms of concurrency. Supersizing our real storage allocation can be an incredibly effective way of improving our performance. We can get a direct benefits in terms of increasing performance and trading increased memory for reduced CPU usage. And of course, the great benefit of that is that unlike a CPU upgrade where you're paying in essentially every month to IBM in terms of the increased CPU usage, by trading that CPU and memory and increasing the amount of memory, it's a one-time cost to buy that memory, and you can permanently push down your CPU utilization during peak hour and potentially reduce your MLC fees to IBM. And of course, Db2 has always had the capability to use as much memory as you're willing or able to provide. So we've gone from this situation where many of us for 5, 6, 7, 8 years had to go on what became known as the Campbell diet, where we're constantly slimming down our use of storage, slimming down the use of virtual storage in order to allow our machines to stay stable and available, and that used to drive up CPU. We can now reverse that effect, throw more memory at Db2, and now that we've got rid of those virtual storage constraints, reduce the CPU and potentially reduce the cost of operating our applications on these platforms. And of course, Db2 offers a lot of possibilities here in terms of being able to utilize this storage. We've got the obvious ones in terms of local and group buffer pools. If you're a heavy dynamic SQL user, as many sites are nowadays, then you can look at increasing the size of your dynamic statement cache in order to reduce the prepare costs for dynamic SQL that's going through application. Log output buffers can sometimes be a gating factor. We can throw more storage there now to reduce the amount of synchronous write activity we've got on our log writes. All sorts of new capabilities in version 12, which we'll get onto in a moment. But let's not forget that Db2 is just one part of the equation, and there are other things: CICS, temporary storage queues, DF sort, ZOS dump space. All of these are very important things for you to consider if you've got some new, additional real storage available as well. Okay, in-memory features in Db2 for ZOS then, in terms of the new features. As I said, Db2.12 isn't a new application anymore. It's been around for a couple of years now. General availability back in October 2016. So we're just about approaching the 2-year anniversary for Db2. And as we said, a lot of the new CPU benefits that are available for version 12 are really around the in-memory features. So the chart on the right of here is really highlighting the standard IBM chart that was produced at the time that version 12 came out. And the top 2 entries in there are the standard LTP workload that this measurement was based against, with and without memory optimization. And you can see a large chunk of the LTP benefits that come from version 12 are really around the memory optimizations we're going to talk about around fast reverse box and contiguous buffer pools. Okay, so let's dive into the detail of this and talk about the first of these major memory features, contiguous buffer pools. And these are really an expansion of the page steal none capability that was introduced back in version 10 of Db2 to allow us to effectively pin data in memory. So when version 10 introduced page steal none, the whole idea is that you could have some dedicated buffer pools which were sized deliberately big enough to be able to hold the entirety of whatever objects it were that you decided to allocate to those buffer pools. So typically we're talking about lookup tables, code tables, commonly referenced objects, high-use indexes, and you would size the buffer pools big enough to be able to completely hold those objects inside the buffer pools and therefore avoid any form of I/O delay, synchronous I/O delay, to any accesses to those objects while they were sitting inside those buffer pools. Page steal none introduced some abilities so that Db2 would read the entirety of the page set into memory when it was first accessed. We had some capabilities in here there to allow the optimizer to make better access path decisions because it wouldn't allow for any physical I/O activity and that kind of thing. So in Db212, page steal none's been enhanced, and we essentially use those buffer pools and treat those buffer pools as a single contiguous memory area inside Db2 now. Db2 is able to avoid the least recently used and hash chain management overheads associated with that because it's treated as a single contiguous buffer. And that means that we get some reductions because Db2 is now able to go away and directly access parts of that data in memory rather than having to go away and look at it as a series of individual get pages. We're able to avoid that get page and release page overhead. We're not maintaining those hash and those LRU chains. And that means that for typical OLTP applications where potentially you're hitting these high access page sets very hard, you can see some fairly significant CPU reductions merely as a result of taking page steal none buffer pools that were previously used in previous releases and making those, continuing to use those in version 12. There's no activity that's needed, there's no rebinds needed, no system configuration needed for using page steal none in version 11. You continue to use page steal none in version 12, but they will become contiguous buffer pools. And in IBM tests, up to 8% CPU reduction was measured for these just in terms of a straight A/B test with the same workload. Of course, I'll make the disclaimer here, for all of these results, your mileage probably will vary in terms of what you see for your workloads, but this is a very quick, very easy win that you can get in version 12. In function level 100, in the equivalent of CM mode, all of your page steal none buffer pools will be able to begin to use these new features. One thing to be aware of is that because we're looking at these as a single contiguous buffer area, Db2 has to allow for the fact that you may have this size too small, and there may still need to be some churn of that buffer pool, some read activity and cast out activity on that buffer pool if the objects you've got in there are actually too big to fit inside the buffer pool. So we do have this separate overflow area now, pages that won't fit in the pool. It's included as part of your VPSIZE allocation, part of your buffer pool sizing, and you need to allow for this because Db2 essentially takes a corner of your pool for this overflow area. It continues to use traditional LRU and hash train processing for there. Your design objective should be very much not to use that area at all and to size your buffer pool big enough to have all of the objects inside the central main area, contiguous area of your buffer pool. The good news is that that's not wasted storage. The overflow area isn't backed by real storage at all. So the fact you have to allow for this in VPSIZE doesn't mean you're going to have storage which is just sitting there and never used. Db2 is not going to physically allocate that storage until it's needed, and your design objective should be never to actually have to use that storage area. So the diagram on the next page here just really shows what I've just been saying. We've got a traditional pre-version 12 page steal null buffer pool on the left here, where we've got individual buffer pool pages being maintained by Db2. We've got LRU chains being maintained by Db2. And even if you're getting no I/O, and therefore Db2 would never need to use those LRU chains, there was still overhead associated with Db2 having to use them. So compare that to the version 12 scenario on the right here, where we've got an identical page steal none buffer pool, but because we're version 12, Db2 is able to treat this as a single contiguous memory area. We don't have the overheads of LRU chain management. We don't have the overheads of individual get and release page activity. Db2 is able to very effectively and directly access areas of storage inside that contiguous buffer pool. And the only difference here is we still have that overflow area shown in the bottom right-hand area of the diagram here, which hopefully you'll never use, but you do need to allow for that in terms of the sizing to make sure your VP size is big enough to hold all of your objects without that overflow area actually being used. And we'll spend some time towards the end of this presentation just looking a little bit in terms of the sizing considerations for that. Okay, so in terms of monitoring, on this next slide here, we're looking here now at some of the new capabilities that have been added for version 12 to allow you as DBAs, as developers, as sysprogs to be able to monitor this particular environment. So our standard display buffer pool command now includes a additional field, which I've highlighted in yellow here, which shows what the overflow allocation is for that particular virtual buffer pool. That is going to depend to a certain extent on the overall size of your buffer pool. We'll come back to that towards the end of this presentation, but I do get to see how big that overflow allocation is. My display buffer pool detail command in amongst all of the information that's traditionally pushed out there also gets this new section here on the DSNB 416i that shows any overflow activity that's happened against my buffer pool in terms of random and sequential get page activities and read IOs. So again, the design point here is for those to be 0 for the majority of the time unless you have exceptional circumstances going on here. All of that same information is included in ifkids02, which is our buffer pool activity within our statistics trace. So you'll be able to go away and use a Megamon or whatever your favorite batch reporting tool is to be able to go away and extract this information for every statistics interval as well in order to figure out how your buffer pools are performing. And finally, and very importantly, we've got this new DSNB 604i message, which is shown at the bottom here, which shows when that overflow area is actually being used for a particular page set. So this is certainly something you should be trapping inside your ops automation package if you're using these things. And under normal circumstances, you should never want any of your page sets to go use this overflow area. It's not an absolute disaster if it happens, but you should certainly have your buffer pool size big enough that this doesn't happen on a regular basis. Okay, and that's about as much as there is to say in terms of explaining the base contiguous buffer pool feature. It's very much an extension of page steal none that was introduced a couple of releases ago. There's some very welcome enhancements there. So moving on to fast reverse blocks, which is where the real meat of this presentation really lies. Fast reverse blocks are really all about producing a memory optimized structure inside DB2 which is meant to decrease the path length for fast random index lookups. So this is all about typical OLTP type of processing here, where you're typically going against a unique index, maybe a primary key, providing a value for that primary key. DB2 is having to traverse the index from the root page through the various non-leaf pages to get to the leaf page. That leaf page will contain the entry for the key that we're looking at and a RID. That RID will allow us to go directly to the data page to retrieve the data. And these index traversals are very, very common in typical OLTP transaction workloads. And fast reverse blocks are all about taking that index traversal from root through to non-leaf, maybe multiple levels of non-leaf and through to the leaf page, and producing a much quicker lookup mechanism for DB2 to be able to rapidly turn a unique key value into the correct leaf page to go away and do the RID page lookup. So we don't get any direct choice in terms of which structures DB2 is going to choose to go away and optimize here and store in this new memory cache. That's very much a choice that DB2 makes under its autonomic transactions. So DB2 is deciding which of these are best going to be cached. And a few restrictions here that we need to be aware of. DB2 has some restrictions here that only unique indexes are allowed. There are a couple of other restrictions here, including key bytes of 64 bytes or less. I will go through the full list of restrictions in a couple of slides' time. So this cached area resides in a special memory area outside of your buffer pools, so you don't need to have any consideration in terms of the sizing of your buffer pools for this, but you do need to make sure you're allowing additional real storage inside DB2 to go away and create this FTB area if you choose to go and enable this feature. So you do need to allow for this as part of your version 12 migration to make sure that you are allowing for that real storage. So this is enabled from V12 M100 onwards, so from function level 100 onwards, the equivalent of the old CM mode in DB2 11. But be aware that if you have group buffer pool dependent indexes, then those will be disabled for FTB caching until you get to function level 500, until you get to after new function activation, because there's a new PLOC that's needed to manage these fast reverse blocks. So there's nothing to stop you enabling this at function level 100, but if you are in a data sharing environment and you are not using partition affinities to limit the workload that's being spread across your data sharing group, the chances are you're going to see much more benefit for this stuff once you get to new function mode at function level 500. And the main control here is this new index memory control ZPOM. That's the thing that actually allows you to disable FTB caching altogether, or if I set it to auto, That's going to enable this caching, and Db2 is going to choose the amount of storage that's in there. And I've said on the slide here, it's going to choose whatever's the largest of 10 meg or 20% of the total size of your buffer pool storage, up to a maximum of 200 gig. So many sites with larger buffer pools, and I know there are a few of you on the call from the survey, are going to be hitting that maximum 200 gig limit here if you've got very, very large buffer pools configured. If you don't want Db2 to size these things and you think you know better and you can size this yourself, then you can actually provide a value here, but we've got the same minimums and maximums here in terms of the 10 meg through to 2000 meg size for the overall storage. So expect that maybe to change in future releases or future function levels of Db2, but for now, that's the range that we're talking about. And as you'd expect, if this is all about eliminating the traversals through an index, typically you'd expect to see the benefits for this increase with a greater number of index levels. And again, internal IBM early testing during the ESP program showed an up to 23% CPU reduction with a 5-level index. So this next slide really just shows what I've explained on the previous one in terms of this caching structure. On the left, we've got the traditional traversal through a 3-level of index in this example, where we've got a unique index here, xsales01, and in order to satisfy the query at the top of the page here, Db2 is going to have to go to the root page, via the non-leaf page, find the correct leaf page, and then using that leaf page, go to the data table. With FTBs enabled, we've got this cached area shown in green, where Db2 is able to take that sales number, that the index key that we're looking for, look it up very rapidly and efficiently in the cache, and go directly to the leaf page that contains the correct key, and thereby straight to the index. So in this case, we've avoided get pages on the root page and the non-leaf page and been able to go directly to the leaf page. Obviously, this is a 3-level index with a 4, 5, 6, 7-level index. Then the greater the number of levels in the index, the greater the potential benefits from this facility. So just spend a couple of minutes on this slide because it is, unfortunately, there's been a bit of confusion in the market in terms of some of these bits of terminology here. And even within some bits of IBM manuals and IBM presentations, these terms aren't really used consistently. So this is my one-man band attempt to try to force some consistency on the industry here and have some consistent terms as to what we talk about when we talk about eligible and candidate and cached. So if we look at this as being a funnel, and at the top level of the funnel in red here, we've got all of the indexes inside a given Db2 environment. A subset of those in green are going to be our eligible indexes. They're the ones that meet the technical criteria for becoming cached in FTBs areas. So the two major ones here being that they're unique indexes, and they have a key size less than 64. There are a couple of others which I'll cover on the next slide, but those are the main ones. So there's our green eligible indexes. We've then got a subset of those in blue, which are our candidate indexes. They're the ones which are being traversed enough in Db2, in any given moment, they're being traversed enough for Db2 to believe that it's worthwhile to go away and cache those indexes inside our storage. So we refer to those as candidate indexes. And then we've got a subset of those, the purple one right at the bottom of the funnel here, that are actually cached in memory. And they're the ones that currently have an active cache structure. Okay, so once again, those are not my terms. Those are not official IBM terms. Those are the terms that I've used that are trying to impose some kind of standardization on how we're actually referring to these things. So I mentioned there are a couple of other restrictions around eligibility here. We know that they're unique. They know they need to have 64 bytes or less. Of course, the indexes need to be open for access. There's no point in Db2 caching an index which isn't actually being used. They can't have multiple versions. They can't be on a catalog table. They can't have timestamp with time zone column in the key. So those are all probably much less important restrictions in terms of day-to-day use, but worth knowing about in terms of the eligibility criteria here for these indexes. I mentioned that these FTBs are actually autonomously created by Db2. So Db2 decides which indexes are going to get benefit and which aren't from being cached in this structure. And that's true, but IBM has given you the ability to at least influence that decision by using this sysIBM.sys index control table. So anyone that's looked at the table that allows you to influence IBM's pseudo-deleted index key cleanup, this is a very similar table for kind of regulating the autonomous behaviors of DB2. So there's some initial columns here for subsystem and partition, an index name, an index creator to identify the particular index. But the key thing here is that action column in the middle here that can be set to F, D, or A. So A is just automatic FTB creation. That's the same that would happen if there wasn't an entry inside this table. D is a way of switching this off for a particular index. So I'm saying disable, and DB2 will not consider any index that's got a D inside it here for being cached. So this is a way for you of switching it off at the index level. F stands for force. It's one of those bad choices, in my opinion. You can't force DB2 to cache an index. All you can do is encourage DB2 to use an index. So I would have preferred to see an E for encourage rather than F for force here. But what this is doing by putting an F there is essentially applying a weighting to DB2 selection algorithm and making it more likely that DB2 will choose this index over and above others. So this is the way you can go away and influence DB2. And if there's a particular index you think there'd be a lot of value and you're not seeing it being cached, one of the options you've got is to go away and try to force DB2 to do so by putting an F in the action column. And the rest of the columns here are really all about scheduling this so that you can have a particular policy in effect, in effect for particular days of the week or hours of the day. Just a quick word warning, duplicates are allowed in here, and DB2 will just use the first row for a given index for a given period. So just be careful that you're not putting duplicates in here and having DB2 pick up a wrong entry. So this chart is really the heart of this presentation, and really defines the heuristics, the process that DB2 goes through in terms of selecting which indexes get cached and which indexes don't. And DB2 is essentially going through this process every 2 minutes. A daemon wakes up and runs through this process in order to decide which indexes will be cached, which cached indexes may be taken out of the structure in order to allow space for new indexes to be cached. Runs as part of DBM1, 100% zip eligible, so no chargeable CPU on general purpose processors being used here. And indexes can drop in and out of eligibility according to the workload. So if you have particular periods where an index is very heavily used, DB2 may start to cache that index, and then if that stops getting used an hour later, that index could easily be removed from the structure in order to free up space for another more highly used index to be used. So if we just follow this flowchart from top to bottom here, DB2 is tracking the traverse count for each eligible index. And a traverse meaning the process of accessing an index with a unique key via the route through a non-leaf through to a leaf page. That's known as an index traversal. DB2 is keeping a count of these traversals for each eligible index. And what it's going to do every couple of minutes, it's going to wake up and say, okay, for this particular index, does the traverse count for this index increase my threshold? And I'll come back to what that threshold is in a minute. If the answer to that is yes, we're going to take the left-hand branch on the decision tree here, and we're going to say, okay, so this is potentially eligible. Have I disabled this index in my sysindex control table? If yes, we're going to discard this index and go back round the loop and look at the next index. If we haven't discarded this index, we're going to add this index to our list of candidates. So it's going to take us down to the bottom right of the candidate list. Going back up now to where we say, has the traverse threshold been exceeded? If we haven't exceeded the traverse threshold, are we enabling our override? Are we trying to force our cache structure inside sysindex control? If the answer is yes, we're still going to add that to the candidate list, even if that threshold list hasn't been exceeded. So that's the impact of our override in sysindex control. So at the end of that, what we end up with essentially is a list of all of our candidate indexes, those that were there by merit because they're being traversed a lot, and those that are there because we forced them in that list because IBM, sysindex control override has actually requested them to be in there. Those indexes are then sorted according to their threshold, with the most frequently accessed at the top and the least frequently accessed at the bottom. And finally, DB2 will then go through a process of either building or destroying those FTBs, working from top to bottom down that list in order to create that particular index cache structure. So back to this traverse count and threshold. So that traverse count is incremented every time a traversal has happened, but there are some things such as random access traversers, sequential access to the index, non-leaf index page splits, which are actually going to decrease that traverse count as well. So if we have an index which is very heavily randomly accessed, is subject to a lot of maintenance, is having a lot of page split activity, then that traverse count is actually going to go down, and potentially it's going to become less eligible to be picked by Db2 for caching. The triggering threshold that we're talking about here in terms of this threshold is reported in IFKID 002. I've given you the field there. It's actually set by a hidden ZPARM inside Db2, and there are some possibilities that might be made adaptive in the future, but it's a fixed hidden ZPARM for the time being, at least in the current maintenance releases of Db2. So this is a vastly simplified version of the algorithm here, but hopefully enough to give you at least a feeling as to the process that Db2 is going through during the selection process for these FTBs. Okay, so in terms of monitoring, then we've got at the system level, in terms of looking overall at the FTB cache, then we've got a DSNI 070I message here, in which Db2 issues to show the fast index traversal status. It shows the total amount of memory allocated to the FTB pool, so it's 20 meg in this example. It shows the number of index which are cached in our pool, 16 objects, and it shows the total number of candidate objects at that stage, also 16 objects. So that corresponds to the cached and the candidate counts inside the filter diagram that we looked at earlier on. So very useful just in terms of knowing the overall size of our cache and the number of objects. This doesn't give us any object level information in terms of which objects are actually being cached. Just finishing off the system level stuff, so we've also got the same information in IFKID 002 inside our stats class 1, and we've got inside that a bit more information in that we get eligible candidate and cached counters here in terms of the IFKID2 fields that I've given you on this chart. So again, use your favorite batch reporting tool to go away and figure out what's going on with these things. Down at the object level, if you want to find out exactly which objects are being cached, we've got this new command now, display stats index memory usage. Glad to say that can actually be reduced to IMU for those of you that don't like typing lots of characters. That will give us a display here of all of the objects that are currently in the index cache, from the biggest object through to the smallest object. So very useful for seeing which specific objects are cached at any moment in time. So we can get that doing a display stats IMU. That information is also in our statistical class 8 in IFKID 389. So we get all that same information in terms of the specific object, the number of index levels it's got, the amount of storage allocated that's being used by this object, and that's written every 2 minutes to our statistics output. And again, you can use batch reporting here to go away and get some information in terms of which objects are being cached during which parts of the day according to your changing workloads. If you do need to, I haven't seen a use for this yet, but I'm sure it will come up. There's a new performance IFKID 477, which is written on the create or free of the FTB for a given index. So if I want to trace exactly when an FTB is being generated and when it's being freed off, then I can switch off this performance IFKID. As always with performance data, be aware it can have an impact in terms of performance overhead for your CPU overhead for your Db2 environment, but also in terms of the volume of records which are written out to your trace output as well. So use with care and use only when necessary. Okay, there is of course a whole bunch of other version 12 related stuff in terms of memory. No time to discuss any of that stuff really on a presentation this short, but I just wanted to make sure that we're all aware that there wasn't just these two features in version 12 which are memory related. There's a whole bunch of new and exciting stuff in version 12 for memory as well. Okay, so in terms of practical guidelines, I'm going to skip, in the interest of time, I'm going to skip over the performance expectations piece. These are essentially charts that I've taken from the version 12 Performance Topics Redbook, and I will leave you to look through these at your leisure, and I strongly recommend if you're on version 12 or looking to get to version 12, that you spend some time looking through that version 12 Performance Topics Redbook. It's the latest in the long line of very, very good performance-related Redbooks for new releases of Db2. It contains a lot of very interesting tests that back up the expectations that IBM set originally during the ASP program in terms of the potential for CPU savings around these in-memory features. Okay, So just moving in terms of some practical guidelines then for these contiguous buffer pools. The guidelines in terms of which are useful remain pretty much the same as they were in version 10 and version 11 for page steal none. So ideally we're looking for objects which are frequently accessed in terms of either high read or high write activity. We're looking for objects which are typically relatively small, but increasingly now as we are able to increase the size of our buffer pools because of increased real storage allocation, going back to the slide that we spent a while on in terms of increased storage being provisioned on Z13, Z14 environments now. Typically there is more storage available for buffer pools. We can make these page steal none buffer pools bigger, and that means we can start to look at caching bigger and bigger objects inside these memory-only objects as well. The third bullet point here is important. These objects typically want to be stable in size. Ideally, we're designing these to be big enough to hold all of the data inside our objects. If that data is growing at 10 or 20 or 30% a month, we're obviously going to have to spend a lot of time in resizing these buffer pools all of the time, and it's not a good candidate. We're looking for things that are relatively stable in size. So typically you see code and lookup tables, critical indexes. These are the sorts of objects which lend themselves best for these kinds of in-memory buffer pools. And there's a very nice feature here in Db212. Our RTS stats, our real-time statistics, now includes get page counters and temporal support. And the combination of those two really makes it much easier for us to be able to identify suitable candidates. The version 12 Performance Topics Redbook that I discussed earlier on has a calculation, an algorithm in there, calculating good candidates for these using get page intensity and the object size. So again, strongly recommend you go look up that version 12 Redbook. It gives some a very nice kind of structured approach for identifying potentially good candidates for these things. I did mention when we were talking about this a while ago that we need to make sure we're allowing in VPSIZE, that we're allowing enough space for this overflow area. And the general rule here is that 10% of that VPSIZE is going to be set aside for the overflow area. That's subject to a minimum of 50 buffers and a maximum of 6,400 buffers. So the chart on the right here basically shows the impact of varying sizes of VPSIZE. If we've got very small VPSIZes here, then we're talking about a big chunk of that potentially being used for the overflow area. As we increase the size of the VPSIZE here, and you know, typically 50, 100, 200,000 would be more typical of what you'd see for these data and memory buffer pools, then obviously the proportion is going down because we're going to hit that maximum 6,400 page size for this overflow area. So just be aware that, for example, if I'm having 100,000 pages in my VPSIZE, only 93,600 of those pages are actually going to be usable for real in data use, because we've got those 6,400 pages which are being reserved out of that 100,000 for in-memory for this overflow area use. So make sure you're sizing VPSIZE big enough so that all of your data can fit in the main area and you're not making any use of that overflow area. That's your design point here. Okay, this next slide, again, it's taken from the Db212 Performance Topics Redbook. It's basically showing the performance impact of overflow, and sure enough, you will see a performance impact as you begin to use that overflow area. Obviously, you're getting a double whammy here. You're having to wait for synchronous I/O because you're not caching all of your data inside the main buffer pool anyway. So that's going to potentially give you a big performance hit. But also, Db2 is having to use LRU and hash chain processing on that overflow area, which means that you're, again, using more CPU to manage those pages than you would otherwise do if you had VPSIZE big enough for all of your data to be sitting inside the main part of that pool. So the message here is very clear. If you're going to use data and memory pools, make sure you're sizing them big enough to be able to cache your objects inside there effectively and not have to use this overflow area at all. Okay, so as we move into the last part of this presentation, then just a few tuning thoughts around fast reverse blocks here. As I said, relatively early. There are customers that are using this for real, but there are relatively few at the moment, and we expect the practical use cases and tuning guidelines here to expand as more and more customers move on to version 12, move into function level 500, and begin to put significant production workloads through these features. So if you are deciding to not set index memory control to auto, remember that's the ZPalm that is used to switch on and off the FTB feature. If we set it to auto, Db2 is going to choose the size of this. If you are choosing to size it yourself, then there's an indication here that your FTB pool might be undersized if your number of index candidates is greater than the number of actually being cached. So remember, the number of candidates is those indexes which technically meet all the criteria. They're exceeding the threshold in terms of the traversal count, but Db2 isn't caching them, and the most probable reason for Db2 not caching them is your FTB area is too small. So if you've manually sized FTB and you're getting your index candidates being greater than the number that are cached, that's a good indication that you might want to go away and increase the size of your FTB pool in order to allow those additional indexes to be cached. Few words of warning. Remember, the law of diminishing returns will apply as you increase the FTB pool. So you might get some great benefit with your FTB pool, say 100 meg, but by increasing that to 150 or 200 meg or further, you may see diminishing returns here as you continue to increase the pool. So you're going to have to look carefully as to whether it's worth increasing the size of the FTB between a certain point, or maybe taking that memory and adding it to buffer pools or to your dynamic statement cache, or even outside of Db2 to another part of your environment. Be aware of percent-free impact. So I have seen at least one customer here where they were getting indexes that weren't getting selected because of the amount of page split activity due to index maintenance. They deliberately went away and pushed percent-free up significantly inside that index in order to reduce the amount of maintenance page split activity that was happening inside there. Of course, the other side of that is to increase your reorg frequency to do the same thing. And by doing that and reducing your page split activity, you can boost the chances of a particular index being selected somewhat. And of course, remember, you've got your sysindex control overrides. Personally, I'm not a fan of these overrides in Db2. It just leaves things open to a DBA maybe going away and putting an override in there for perfectly valid reasons, but then maybe 6 months or 9 months later, when the DBA has moved on to a new role, has left the company, and people are scratching their heads trying to figure out why Db2 is behaving in a certain way, it's because somebody thought it a good idea a while ago to go away and override these autonomics, and that really can come back and haunt or bite you later on.
Weird troublemaker.
Another common frustration when you're getting into FTBs for the first time is that you think that an FTB is a good candidate, it meets all the technical criteria, but you're just not seeing them being cached when you go away and look at the structures being cached by doing your display IMU. So what I've listed here are the most common reasons why a given index won't be cached. I don't think this is completely exhaustive, but in my experience it covers by far the most common reasons for a given index not being selected by Db2. Top of the list being the traverse count not meeting the threshold, so you're not having enough random access, or you're doing too much sequential access or too much page split activity, and that's driving down that traverse count, which means it's not making the cut in terms of Db2 looking at the most valuable indexes. Be aware that Db2 has got its own internal limit of 10,000 indexes per member that it can actually cache at the moment. That's an internal limit that can't be changed. There's also the overall size of the structure that you provide via index memory control if you're not using auto for that setting. Db2, if it detects a significant amount of paging going on the system, it's going to disable FTB creation, so that could be another problem. If your function level is less than 500, so if you're not in new function activation and the index becomes group buffer pool dependent, then that index will not be considered for FTB creation. And there's a few others here in terms of the index being stopped, or utility access, or any kind of master delete processing. So be aware, if you're kind of banging your head against a wall and you can't figure out why, it's likely to be one of these reasons that it isn't caching their index. Okay, so a lot of material to cover here inside 45-50 minutes, so I apologize for speaking quite quickly. Hopefully if I spoke too quickly, you'll be able to go back to the rerun and slow me down and understand a bit better what I was saying. The takeaway message here is that the industry is moving in a clear direction here. IBM is moving in a clear direction here in terms of bigger memory per LPAR, bigger memory per KEK. Db2 is moving aggressively to use that bigger memory, and things like fast reverse blocks and Db2 contiguous buffer pools are very quick wins in terms of being able to grab some additional real memory allocate it to these objects. No application changes required, no system changes required, and you can begin to very quickly exploit this new memory to drive down CPU and potentially drive down your MLC fees. And my last point is make sure you're talking to your ZOS sysprogs about any unallocated memory you see. I see in many, many customers I go to, I see unused memory unallocated memory being used on LPARs, which drives me bonkers. If there's memory that's onside that KEC that could be used, that Db2 could be using to drive down your CPU, you should absolutely be making a case to go use that memory and potentially reduce your MLC fees to IBM. So that's pretty much all I have, Martin. So I'll hand it back over to you to wrap up.
Well, thanks so much, Julian. That was a great session. I had one question in, and actually it wasn't relating to content, but it was really interested in whether or not you'll make your slide deck available.
I will absolutely make the slide deck available. Yes, no problem whatsoever.
Great. So everyone knows where the replay blog is at db2nightshow.com. That's a subset of the DBI website, and you'll be able to go on there and find the replays and find this. I have to post-process it. I'm hoping to have it done by 5 o'clock Eastern time, this afternoon, Eastern North America time. And so you'll be able to find that out there, as well as the information for registering for our next two shows. So that was absolutely fantastic, Jules. Let me take control over. I'll just pop up my screen here and find myself. There we are. Make a presenter. Show my screen. Now you should be seeing the screen, and I will ask the last polling question, which is our standard question, which is, did you learn something today? We'll launch that right now and let people give us a quick vote on that. And responses are looking as expected here. People are voting quickly. People have paid quite a bit of attention. I found your presentation very clear and very easy to follow, Jules. That was absolutely great. And with that, I think we've gotten the answer we want to achieve. So I'll close that and share that result with everyone, which is wow. 100% of our audience today learned something. We love to see that because it means we're hitting the mark with our audience. And I went through the list of the audience, and I saw some very experienced old friends that were tuned into the audience today. People from the Netherlands and Germany and other places like that. So shout out to Wolfgang and Dewey and people like that. So it's fantastic to see people online. And of course, we've also always got our fans in California as well that get up a little earlier and also check in. So that's great to see. So with that, I'll hide that and come back over to our slide deck. Hopefully it's showing. There is a survey that we have at the end. Please complete that. Let us know how we're doing and watch the replays, as always, at db2nightshow.com. One final word on the show being sponsored by DBI. They make the webinar environment available to us ZOS folks, even though they're an LUW company, and we're grateful for that. And with that, I look forward to seeing as many of you that can make it to Malta next month. I'll be there speaking myself, and safe travels to all going there. And we will see you after Malta, back for the next DB2 Night show on the ZOS edition. And with that, I will cue the music, and we will thank Jules one more time, and here comes the music. Take care. Have a great weekend, all. It's getting a little chilly here, but that happens in November in Canada. And all the best, and we will see you next month. Bye-bye.